lesson videos, we learned the concrete pressures and it applied for the vertical forms, which is row and column forms. Now we want to uh, go to determine the design loads for the floor and roof slab forms, and then move on to the last problems of today's lesson to design for the slab forms. So let's go to the load that we apply for the floor and slab forms. So that slab form is horizontal, so the load it will be vertical. Vertical. How to determine? Same at your structural analysis class, the design load equal to the dead load plus live load. So what is the dead load and what is the live load? In this case, the dead load, it will be the concrete on the formwork and the dead load of the formwork itself. So those are the two major dead load. The live load, the people, the worker working on it, the equipment run on the temporary structure and the formwork. And how to determine the live load? In this case, if it's no motorized, no machine working on the formwork, then the live load at least 50 pounds per square feet, per square foot. If it have motorized carts involved working on that formwork, then at least 75 pounds per square foot. And the design load, that including that load and live load, at least 100 pounds per square foot. If no motorized cart, and 125 pounds per square foot if motorized cars are used. And like I say, these vertical loads apply for the floor and slab. So don't be confused with the load that concrete pressure apply when we design for the columns and the walls. So the method of analysis is same as we learned in the mechanics of material, structural analysis, concrete design, and steel design. We need to determine with regard to bending, determine the structure with regard to shear, compression, tension, and deflection. And of course, we don't have to always consider all of that. For example, if we learn the columns with a central axial load, then it only compression and the bending, in this case deflection, that we are method, right? For the beams, it may need only the bending, the shear, and the deflection. Don't need to be compression for the beams, as you can see, unless it simple beams it may have, but continuous we can ignore that, compression and tension. So bending, shear, and deflection. And like I say, we focus on the slab form design, and that is the objective for today's lesson. Let me go to show a few form and then go back to the final exam reference before we go to problem 3, the last problem in today's lesson. So you have the typical form here, and this is for slab and beam, as you can see. So the vertical load, design load, live load is going down vertically, as you can see there. So including the concrete, we are going to place the load of the formwork itself, that is the dead load. The live load is the worker working on it, and then the motorized equipment on it as well. So with that, the typical setting of the formwork for slab and beams, we have the sheathing, and this can make it from lumber or plywood, so engineered products. And then we have a joist, and there's space in there. And then we have a stringer. Here they call beam, but we can call stringer. And then we have the shoring, something we already talked. And then we have the bracing to ensure it will not have the can withstand with the lateral forces. So with that, we can, in the slab form design, we need to design for the sheathing to check that whether space is okay, or what should be the space between the stringers, between the joists, so that sheathing is working fine. And then go to design for the joists. We need to know the space between the stringer, and then go to the die stringer. We want to determine space between the shore. So that is the process we have. So it always starts from the top, the seed and then the choice, then the stringers, and then the short. So depends on the way it works. As you can see, for the slab or for the stringer or for the choice, what is the support condition we have, and then the moment are different, and that just based on your mechanics of material, you can be able to determine deflection, the maximum moment, and the shear. And then with that one, and this is the table that we use a lot and that I'm going to explain in here to determine the sitting, stringer, or the choice for the formwork. So, and I can see for the beams, and we can model it at a beam, even in the sitting. And that we need to check the design condition for bending, for shear, and for deflection. In bending, the equation are different, depends on the material, whether it's natural wood or plywood. So for plywood, engineer products, we use these equations, but that depends on what is the support condition. If only one single span, you can see that equation. If it two spans, that equation for bending. And if three or more, that tend to be the case, then you apply in the last column there. If it's good products, then you have two equations. Depends on it's the similar equation, but the conversion. I give you example here. FB stands for the allowable stress for bending, FB. And then B is the width of the members. W is the uniform distributed load on the members. And the second equation is at BS. So S is stands for section modulus, that you know. So depends on you have B or S, then you apply either two equations, should get the same answer. For wood, for plywood, you have. Similarly for the shear, and it apply for wood or plywood, you have two different equations, depend on the support conditions. And then deflection depends on what is the tolerance to have. If it deflection is over 130, it means you allow higher deflection. If it's more stringent on the deflection, 1 over 360, the equation are not the same. And that just go back to your knowledge. Where this equation come from? Basically, come from your mechanics of material. And then compression and tension, we can apply that in here when we check the crossing, etc., between the members. So we will do that in problem 3. But let's go continue further here. Section properties. When you go to law, etc., we need to see the section properties of different materials and with different properties with the EI. So the E stands for section modular rigidity, right? I stand for the area moment of inertia. So you have on a different plywood that you can see here what is the section property should be, so that you can go back if it plywood, not lumber in this table. We can go back to apply the plywood for this equation with different section properties of the plywood. Depends on the thickness, as you can see here, and what each class of the plywood form should be. The about the lumber, and in the lumber, the nominal size and the actual size are not the same, so keep that in mind. For example, here, if we're talking about the plywood with the thickness, you go to Lowe's or Home Depot, buy the lumber with the thickness nominal is 1 inch. Actually, the actual thickness only 3/4 of inch, so 0.75, as you can see there. And similarly for different sizes, if it's like 3x4, which is the width is 3, the depth is 4 nominal, it becomes 2.5 times 3.5 actual size. And when you design, you have to design for actual size. So you use table to determine the section properties. The last one, sometimes the problem. Don't give us the FB, FV. What is FB, FV? We will discuss that in the reference in a minute. So FB, allowable compression for bending. FV, allowable compressions for shear. FC, perpendicular, allowable stress in compression perpendicular to the grain. So as you can see, for lumber is not homogeneous and isotropic throughout. Different direction have different strength, and that you can see perpendicular to grain and parallel to grain are not the same. Tension and Young modulus or modulus of elasticity. And a different type of material of the different type of wood or lumber you have. Douglas fir, hemlock, southern pine, California redwood, Aspen spruce. They have different time of unit stress that you can have in there. And of course, it also have reduction factor for the wet condition. If the load duration is 3-day load or more, so then you can have to consider that as well. So if the problem don't give you the FB, FV, then they may give you what type of material, what type of wood is that. So you can go back to this table you have. So before go to problem 3 again, I go back to the reference so that you get familiar with that. The final exam reference. Here, the table we have on of that table that I just showed you, and this is determine the allowable unit stress for different type of lumber. And then we have the concrete form design equation for different situation with the support condition, with different design condition, bending, shear, or deflection. And this that I'm going to talk about, if you forget what is the symbol or notation, go back to this table on page 5 of the final exam reference. You can find out section properties of plywood. If the problem give you plywood, get that information from here. And then the section property of the US standard lumber and timber, you can get it in here. So give you the actual size, area section, so the area, the section modulus that need in that, and then moment of inertia. So those are the equations that you can be able to, the table that you can be able to use to design, and let's apply that in problem 3.